We're going to look at some affine geometry. This is really just the geometry of lines and planes. First, we're going to recall the distance formula. Then we're going to look at lines. In particular, we're going to think about parametric descriptions of lines. We're also going to take a look at planes and recall the parametric description of planes that you've seen from linear algebra, although perhaps not using this language. We'll also see how we can describe planes using linear equations. Finally, we'll give formulae to solve certain distance problems that we care about in affine geometry. For further reference, you can check out sections 1.2 and 1.5 in the course textbook. So we start with the distance formula, and our first observation is that the distance between any 2 points, P and Q, is the same as determining the magnitude of the displacement vector from P to Q. Here's an example. If you have any questions, then just let me know, and I'd be happy to work through this. The distance formula satisfies several properties. First property is that the distance between P and Q is equal to 0 precisely whenever P is equal to Q. It would be impossible to have 2 points which are not the same point which have 0 distance between them. Secondly, we'll observe that the distance function is symmetric. Namely, the distance from P to Q is the same as the distance from Q to P. And finally, we record the triangle inequality, which states that the distance from P to R is always less than or equal to the distance from P to Q plus the distance from Q to R. Now we'll look at lines. So the line is one of the most basic geometric notions. For us, a line will be unbounded and extend infinitely in both directions. A line segment will be a connected subset of a line that is bounded. By that I mean bounded in both directions. Or another way of saying this is that a line segment will live in some box. It could be some huge box, but it's some finite sized box. Finally, we'll also talk about rays. An array is a subset of a line that is bounded in one direction only. So we can define a line or a line segment or array using two pieces of information. We need to determine a point P on the line, line segment or array, and we need a direction. Of course, now we know that whenever we want directions, we really mean we want a displacement vector u. Given this information, this leads to a parametric description of the line. This is the parametric description. Here t is the parameter and I is some connected interval, subinterval of the real numbers. The difference between a line and a line segment and array is determined by the values that we allow the parameter t to take. So here I'd like for you to stop the video and try and see if you can match up the type of line with the corresponding interval I. Okay, so we see that, well, a line should be infinite, so the parameter should be allowed to be any real number. It should be infinite in both directions. Similarly, a line segment is going to be bounded, so our parameter is going to be bounded. It's going to lie in some bounded interval. Finally, a ray is going to correspond to a subset of a line that's bounded in one direction only. So this means that our parameter must live in a semi-infinite interval. So here's an example of the parametric description, a visual interpretation. So we see we have a point P and our direction vector u, and we're giving our parametric description we're saying that we're starting at the point P. We're using the position vector of P for our starting point, and then we're moving in the direction of U. And T you should think as a time. So after one time step, we will have moved 1 unit in the U direction. Similarly, after 2 time steps, we would have moved 2 units in the U direction, and so on and so on. When T is a negative number, this means that we're going back in time. Or another way of saying this is that we're going in the reverse direction along the line from the point P. So here's an example to determine the parametric description for a line passing through 2 points inside space. Again, I'll let you work through this example on your own, and if you have any questions, then please let me know. One thing to note here is that these equations we have at the end are what we call parametric equations of the line. We will investigate further parametric equations when we come to describe parameterizations of curves. In fact, you've already seen some parameterizations in the previous video when we were looking at the cycloid example. So now we move on to planes. So recall from linear algebra that a single linear equation in 3 unknowns determines a plane. Of course, here we need that at least one of A, B, and C is non-zero, because otherwise we don't really have an equation at all. Here's a plane. So for example, we could consider the following equation. So in linear algebra, what you would have done is to determine the solution set of this equation. You'd have written one of the variables, the dependent variables, in terms of the remaining free variables. You would have obtained possibly something that looks like this piece of mathematical notation here. If you have any questions about this, then please just let me know and I'd be happy to work through this. Here, this tells us that, in fact, the solution set to this equation is a plane that is parallel to the plane that's spanned by these 2 vectors, -2, 1, 0 and 5, 0, 1, and which passes through this point -3, 0, 0. You may have also seen the terminology, we have a particular solution, i.e. we have a fixed point that is a particular solution to this equation, and then we have all of our homogeneous solutions, and that's given by the slit corresponding to the plane spanned by these 2 vectors here. So this is really, in fact, completely analogous to the parametric description of a line that we've given before. Here we see, in fact, that x2 and x3 will actually be our parameters in analogy for our parameter t for our line. The problem, of course, is that because we have 2 independent directions to move in on a plane, you can't really talk about time in the same way that you can talk about this for a line. So a basic question is, how can we find an equation that defines a plane? For example, let's suppose I gave you a parametric description of the plane. How could we determine an equation that defines that plane? Well, inside space, planes are perpendicular to lines. So in particular, this means that we can always find a vector which will be perpendicular to the plane. In fact, we call this vector the normal vector. So now we see that given a plane, pi, if we have any point on the plane, P, then any other point Q on the plane must satisfy that this displacement vector PQ is perpendicular to the normal vector. We can write this using the dot product. And then after a bit of rearrangement and recalling how we compute displacement vectors, we've led to the following equation. I'll let you have a think about this, and if you have any questions, then please let me know. So here's an example. We'd like to determine the equation of a plane that contains three non-collinear points P, Q, and R. So you may remember from high school that any three non-collinear points, by that I mean 3 points in space that do not lie on this common line, determines uniquely a plane. Well, to determine this plane, all we need to do, given our previous discussion, is come up with a normal vector and then plug this into our expression that we've found on the previous slide. So I'll let you work through this example. If you have any questions, then just let me know. So finally, we're going to record a couple of formulae for two distance problems. So the first distance problem that we're going to be interested in is trying to determine the distance between a point and a line. So given a line L with the parametric description and any point Q need not necessarily be on L nor not on L, then the distance from L to Q is given by this formula. I'll let you think about this geometric picture that I've given you here, and if you have any questions, then please let me know. Secondly, we have a distance formula for the distance between parallel planes. If we have two planes, pi1 and pi2, and when we mean that they're parallel, we mean really that their normal vectors are parallel. And if we take a normal vector for pi1, then we can determine the distance between these two planes as follows. Here we have to take 2 points on these planes and determine their displacement vector, and then consider their dot product with our normal vector. Again, this is just an application of some geometry. If you have any questions about where this formula comes from, or anything on the diagram, then please just let me know.